Alright, let's take a look at some derivative rules. So we stated that the derivative is basically the instantaneous rate of change function to a point of x. It's also the slope of the tangent function, right, to a point of x. And there are a few rules that govern derivatives. I've kind of summarized the four major rules outlined in this video. So the first rule we're going to be looking at is a constant rule, where f of x is equal to some kind of constant. Then we're going to be looking at the power rule, which is really common for polynomials, right? Then we're going to also take a look at the constant multiple rule, right, where f of x is equal to some constant times a function. And then we're also going to take a look at the sum and difference rule, which I kind of collectively expressed it because it's really the same notion, where h of x or some kind of function can be written as two or more different functions. Okay, so let's take a look at the constant rule, and I'm going to be doing examples for each of these rules. And when we're looking at the derivatives, we're going to be using these two types of notations. We're going to be looking at the Lagrange notation, which looks at the derivative as using the symbol prime, right? So the first derivative of a function f of x is f prime of x. The second derivative is f double prime of x, and so forth. We can also take a look at this in terms of Leibniz's notation, which basically expresses the derivative as the rate of change of y with respect to x, right? And the d represents a small incremental change, right? I like the Leibniz's notation because of the modifier, the derivative modifier dx, right? It just means to take the derivative of something with respect to x or whatever the denominator's value is, okay? So what I'm going to do is I'm going to do an example for each of them. Let's start with the constant rule. So using the constant rule, f of x is equal to a constant. Let's say f of x is equal to 5. Okay, using Lagrange's theory, the derivative function f prime of x is equal to the derivative of that constant. I'm going to use Leibniz's notation, the the modifier ddx of 5, or the rate of change of 5 with respect to x, and the rate of change of any constant is 0. Okay, and the reason for that is because when we have a constant on a graph, like for instance, if this is 5, this is y is equal to 5, the slope of the tangent at any point on this graph is going to be 0. Okay, take a look at the power rule. So let's say f of x is equal to 2x to the power 2. Okay, the derivative f prime of x is basically the power n times a, which is 2 times 2, which is 4, x, and then we subtract 1 to the power. So this is 4x to the power 1. We don't have to write the 1. Okay, and you can see the same thing being written in Leibniz's notation. I'm just kind of incorporating the two together, right? But I do like this modifier, the derivative modifier that is incorporated by Leibniz's notation, because it shows you exactly what to do, what you're doing, right? So it's a good way to just kind of show your steps. Let's take a look at the constant multiple rule, where f of x is equal to some kind of constant times g of x. When you're doing the derivative, you can actually write the constant on the outside. So this is kind of exemplified using Leibniz's notation. You can see that the constant is kind of taken away, and then you can do the derivative of the inside, right? So in this sense, let's say we have f of x is equal to 5x to the power 4, right? F prime of x is basically equal to 5 times the derivative of x to the power 4, which is 5 times, and I'm going to use power rule again, 4x cubed, which is basically 20x cubed. Okay, so it's kind of similar to the previous example, right? It just tells us that we can take the constant out and then do the derivative of the function by itself. The last rule here is the sum and difference rule, right? Where if h of x is made up of two or more different terms, right? The derivative is the derivative of all the terms, right? And in this case, let's do h of x is equal to negative 3x squared minus 4x. Then h prime of x is equal to the individual derivatives of each. So the derivative of negative 3x squared minus the derivative of 4x. And then if you employ the power rule, you get negative 6x minus 4. Okay? Yeah, those are some of the derivative rules which we're going to be using to do questions in the future. Alright, let's differentiate the following with respect to x. And if we consider part A, where f of x is equal to the cube root of x, we're going to differentiate using the power rule. So to use the power rule, I need to change this radical into an exponent. Now we can understand the conversion where if x is a base to a power x a over b, then we can rewrite the exponent as x to the power a to a root of b, right? And b is the index and a is the power on the radicand, right? So what you want to do, if you convert this radical in the form of an exponent, then you can rewrite this as f of x is equal to x to the power 1/3. Then using the power rule, we know that if f of x is equal to ax to the power n, f prime of x is equal to a times n x, and you subtract 1 to the power, so n minus 1. So using this notion, right, f prime of x is equal to 1/3 x, 1/3 minus 1, which is negative 2/3. Okay, if you wanted to write this as purely positive exponents, you can write this as 1 over 3 x to the power 2 over 3, right? And this is perfectly fine as well. Okay, so this is your derivative. Okay, let's take a look at part B. So part B, we have y is equal to square root 3 x square root 2 to the power of square root 2. And what you want to figure out here is dy over dx, which is the rate of change of y with respect to x. And once again, we're employing power rule. The only difference is that the power, instead of having a concrete natural number, we actually have an irrational number in the form of a radical, right? But we still employ the same rule. So we do square root 3 times square root 2, right? So square root 3 times square root 2, and you can use the radical rules where you multiply the radicands, and then x square root 2 minus 1. So this is basically square root 6 x to the power square root 2 minus 1. And the thing is, you can leave your answer like that because of the fact that square root 2 is rational and it's going to contain decimals. So this is actually going to be more exact. And that is the derivative of the following. Alright, let's differentiate h of t is equal to a plus b over t plus c over t squared if a, b, c are constants. So the way we're going to differentiate this, we're going to differentiate this using the power rule. So once again, the power rule, if f of x is equal to a x to the power n, f prime of x is equal to a n x n minus 1. Okay, now you can notice here that this is there's multiple terms, there's 3 terms. So in this sense, we're going to basically be using the sum and difference rule of the derivative. Okay, so just kind of review in the previous videos where we actually looked at some of these differentiation rules, and specifically power rule in general. Okay, so if I was going to find the derivative of h of t, right? What I want to do here, just to make my life easier, I'm going to change all of these reciprocal fractions in the form of powers. So I can rewrite this equation, h of t, as a plus b t to the power negative 1, right? Plus c t to the power negative 2. Okay? Now we need to note here that I'm basically using the rule as x to the power negative a is equal to 1 over x to the power a. It's an exponent rule, so make sure you know this. And if I'm finding the derivative, h prime of t is equal to the derivative of a with respect to dt plus the derivative of b to power bt to the power negative 1 respect to dt, or the rate of change of t, plus d dt c t to the power negative 2. Okay, so you're doing the derivative separately, right? I'm just using Leibniz's notation as well as Lagrange's notation. It just kind of shows my step process. Now here we have the derivative of a constant, which is 0. Okay. Now if we use power rule here, we get negative b. Okay, so you do negative 1 times b, so negative b, t to the power negative 2, right? You subtract 1 to the power. And then for the next term, we do negative 2 times c, so negative 2c, t to the power negative 3. Now if we only wanted to use positive exponents, this would look like negative b over t squared minus 2c t cubed. And that is basically your derivative function. Alright, let's simplify and differentiate the following function, p of x. So p of x is equal to x to the power 8 minus 4x to the power 6 plus 2x cubed over 4x cubed. Now you can notice here that 4x cubed is dividing all of these terms. So I'm going to simplify this guy out. And I'm going to rewrite my function as x to the power 8 divided by 4x cubed minus 4x to the power 6 divided by 4x cubed plus 2x cubed divided by 4x cubed. Okay, and in this case you're going to get 1 over 4, right? Well, you can write this as x to the power 5 over 4 minus 4 divided by 4 cancels out. X to the power 6 divided by x to the power 3 is x to the power 3, right? So you're just using exponent rules here, right? Same basis, when you're dividing you subtract the powers. And then you do the same thing here, plus 2 over 4, x to the power 3 divided by x to the power 3, cancels out. And now you're left with x to the power 5 over 4, or 1/4 times x to the power 5, minus x to the power 3, plus 1/2. And this is what your function p of x looks like, right? And then what you want to do here is you want to find the derivative. So p prime of x is equal to, I'm just going to be using the combination of the difference and the sum rule. So the derivative with respect to x of 1/4 x to the power 5 minus the derivative with respect to x, x cubed, plus the derivative of 1/2. Okay, so this is going to basically give you 5 over 4 x to the power 4 minus 3x squared, and then this is 0. Okay, and then this is your derivative function p prime of x. So it's not too bad. You just have to kind of simplify this out first, and it makes the question a lot easier. Let's say we want to determine the derivative of the following. P of a is equal to a to the power 5 over 15 minus 2 times square root a. Just to make our lives easier, let's change all of this to an exponent wherever possible. So what I mean by that is I want to change the radicals to exponents. Minus 2 a to the power 1/2, right? Because a to the power 1/2 is square root 2. And then if I want to find the derivative, you can notice here that we're using the difference rule here, right? P prime of a is the derivative of, right? So don't memorize the modifier, because the modifier here is the derivative of y with respect to a, right? Of a to the power 5 over 15 minus 2 derivative d dA a to the power 1/2. Then you use the power rule, right? So if we use the power rule, we're basically going to get 5 over 15, right? Because you got to think about this as 1 over 15 times a to the power 5. And then when you do the derivative of a to the power 5, then what you're going to get here is a to 5a to the power 4, right? So I think it would be easier if we kind of wrote it like this. 1 over 15 d dA a to the power 5. Okay, and then you can just do the derivative of a to the power 5 anyways. So that's going to give us basically 5 over 15 a to the power 4 minus 2 times 1/2 a to the power negative 1/2. Okay, so I'm just utilizing the power rule. And in this case, p prime of a, if I clean up some of these terms, you should get 5 over 15, which is 1 over 3. Let's make this 1 over 3. A to the power 4 minus 2 times 1/2 cancels out. A to the power negative 1/2. And if you want to keep positive exponents, we have p to the power p prime a is equal to a to the power 4 over 3 minus 1 over a to the power 1/2. Or you can do square root a. Right? And you can leave your answer like this. Okay, and that's the derivative. Okay, so let's take a look at another rule of differentiation. This is something called the product rule. So you would utilize the product rule when you actually get a function which is the product of two or more functions. Okay, so if p of x is equal to two terms or two functions, f of x times g of x, then the derivative of that function p of x, p prime of x, and I'm using Lagrange's notation to demonstrate that, is equal to f prime of x times g of x plus g prime of x times f of x. So you do the derivative of one of them times the other plus the derivative of the other times the other guy. Okay? And you can also express this using Leibniz's notation, right? So you do derivative, right? The derivative modifier, derivative of a function with respect to x, right? So you do derivative of g of x times f of x plus g of x times the derivative of f of x. Okay? Either way, both will mean the same thing, right? So we'll just use a combination of the two. I tend to use the derivative modifier, d dx, or the rate of change with respect to x, right? Because it just kind of clearly shows that we're finding the derivative of something. It's my derivative modifier. Okay, so this is just a great way to kind of just show your work. So I'm going to just show you guys an example really quickly. Let's say we wanted to differentiate this equation of g of x. If we want to find g prime of x, if we're using the product rule, I'm going to do the derivative of the left factor. I'm going to clearly state this by using the derivative modifier, x squared plus 2 times the right factor, 4x minus 5, plus the left factor, x squared plus 2, times the derivative of the right factor, 4x minus 5. So you can kind of note that I'm using a combination of Lagrange's notation as well as Leibniz notation. Really means the same thing, right? But it's a great way to kind of just show your work. So the derivative of x squared plus 2 is 2x times 4x minus 5 plus x squared plus 2 times the derivative of 4x minus 5, which is basically 4. And this is your derivative function, g prime of x. And then I'm just going to expand this guy out. So you get 8x squared minus 10x plus 4x squared plus 8. And this is g prime of x. Right, and then you can just kind of collect the like terms. So g prime of x here is equal to 8x squared plus 4x squared minus 10x plus 8. In this case, you get 12x squared minus 10x plus 8. And that's basically your derivative function. Okay? Alright, let's do an example of where we would use the product rule. So I want to determine f prime of negative 2 for f of x is equal to negative 5x cubed plus x times negative x plus 2. So once again, because it looks like a product of two different functions, f prime of x, using the product rule, is equal to the derivative of the left factor, negative 5x cubed plus x times the right factor plus the derivative of the right factor. And remember that multiplication is commutative. That means that we can reverse the order and still get the same value. Like 3 times 4 is equal to 4 times 3. So it doesn't really matter if we change the order up. Times negative 5x cubed plus x. Okay, in my next line I'm going to basically simplify and find the derivative of each of these. So negative 5, derivative of negative 5x cubed, so you do 3 times negative 5, so negative 15 x squared plus 1 times negative x plus 2 plus derivative of negative x plus 2, negative 1 times negative 5x cubed plus x. In this case, you basically, if you expand this out, you get 15x cubed minus 30x squared minus x plus 2 plus 5x cubed minus x. So this is f prime of x. Right, and you just collect all your like terms. You get 15x cubed plus 5x cubed minus 30x squared minus x plus 2. Okay, and then you just kind of collect all the terms. You get 15x cubed, collect the 15x cubed plus the 5x cubed, sorry about that. So this is 20x cubed minus 30x squared minus 2x plus 2. Okay, so that's your derivative function, but you want to find the first derivative when x is equal to negative 2. So you're doing f prime negative 2, or the slope of the tangent when x is equal to negative 2, which is 20 times negative 2 cubed minus 30 times negative 2 squared minus 2 times negative 2 plus 2, which is basically 20 times negative 8 minus 30 times 4 plus 2. And that's going to give us negative 160 minus 120 plus 6, which is basically negative 280 plus 6, which is negative 274. Okay, this is a really steep slope. It's a really steep negative slope, but that's our value in that sense. Okay. Alright, let's determine the equation of the tangent to the curve. P of x is equal to negative x cubed plus 2 times 4x squared minus 3 at x is equal to 3. Okay, so to find the slope of the tangent, we need to find the derivative function. So it looks like we're going to be employing the product rule here. So p prime of x is equal to, I'm going to do the derivative of the left factor, or the factor at the left, negative x cubed plus 2 times 4x squared minus 3 plus the derivative of, and I can change the order because multiplication is commutative, so you can reverse the order and still get the same value, 4x squared minus 3 times negative x cubed plus 2. Okay, and in this case, if I find the derivative and clean this up, derivative of negative x cubed is basically negative 3x squared times 4x squared minus 3 plus derivative of 4x squared minus 3 is 8x times negative x cubed plus 2. And then the derivative function p prime of x is equal to negative 3x squared times 4x squared is negative 12x to the power 4 plus 9x squared minus 8x cubed, to the power 4, 8x to the power 4, because this is like x to the power 1 and this is a 3, right? And plus 16x, okay? Now we want to collect all the like terms, so the only two like terms I see is negative 12x to the power 4 minus 8x to the power 4 plus 9x squared plus 16x. So collectively, your derivative is basically negative 20x to the power 4 plus 9x squared plus 16x. Now we want to find the slope of the tangent at x is equal to 3. So this is the general slope of the tangent equation. To find the slope of the tangent at x is equal to 3, I'm going to do p prime of 3, which is negative 20, 3 to the power 4 plus 9 times 3 squared plus 16 times 3. And in this case, you get negative 20 times 81 plus 9 times 9 plus 48. Okay, and if you input this in a calculator, you're going to get a really steep negative slope, negative 1491. Okay, so that's your really steep negative slope. So now we have the equation of, we have the slope of the tangent, it's negative 1491 x plus b. If you want to solve for the y-intercept, we need to find the equivalent point at x is equal to 3 for y. Okay, so we need to find the equivalent y value. So if we know that the point is going to be 3 NP of 3. Okay, whoops. And in this case, what we want to do is find p of 3. So p of 3 here is basically negative 3 cubed plus 2, 4 times 3 squared minus 3, which is negative 27 plus 2, and 36 minus 3 is 33. So that's going to give you negative 25 times 33. So yeah, we do have a set of large numbers here. So that's going to give you negative 825. Okay? So p of 3 is negative 825. So the collective point is 3 and negative 825. Okay? And then we just substitute this in. So when we sub this into your equation, okay, we plug this in for y. So negative 825 is equal to negative 1491 times 3 plus b. And then if I crunch all this out, so 1491 times 3 gives us negative 4,473 is equal to negative 825 plus b, and then I'm going to move this to the other side. So b here is equal to 3,648. Okay, so yeah, these numbers are kind of extreme. Okay, but now we have our equation, so y is equal to negative 1491x plus 3,648. Okay, so this is the equation of our tangent. Okay, find the derivative function. So if we look at this function, y is equal to x plus 5 times 7x minus 2. In this case, we have to actually use product rule. So if we're using product rule, the derivative function dy over dx is equal to, I'm going to do the derivative of the left hand factor. So derivative of x plus 5 times 7x minus 2 plus the derivative of the right hand factor, 7x minus 2 times x plus 5. I'm going to simplify this. So dy over dx is equal to derivative of x plus 5 here is 1 times the rightward factor 7x minus 2 plus derivative of 7x minus 2 is 7 times x plus 5. In this case, you get 7x minus 2 plus, I'm going to expand this out, plus 7x plus 35. And then group the like terms together. So if I group the like terms together, I get 7x plus 7x minus 2 plus 35, which is 14x plus 33. Okay, so this is basically your derivative. Alright, now we're going to look at another rule of differentiation, and this is called the chain rule. The chain rule is really common or really useful when we have a composite function. So a composite function is basically when we have a composition of two or more functions. That means a function within a function. For example, if we have f of x is equal to g composed of h of x, where h of x is a function within g of x, right? So g of x is actually composed of h of x. The way you'd write this is you write this as g composed of h with respect to x is equal to g of h of x, right? Likewise, if you wanted to do it the other way, if you had h composed of g of x, then you would have h of g of x, okay? If you still do not understand what a composite function is or where it can be applied, take a look at some of my other videos regarding composite functions. Anyways, if you wanted to find the rate of change or the derivative of a composite function, let's say we wanted to figure out f prime of x, and f prime of x is composed of g and h of x, right? So if f of x is composed of g and h of x, then f prime of x is g prime of h of x times h prime of x. Okay? So I'm going to show you guys how to use this notion. So let's say that we have y is equal to the fifth root of 2 plus 3x squared minus x cubed. We want to find dy over dx, right? So in this case, we can rewrite y, and I'm just going to use exponents for this. You can write this as 2 plus 3x squared minus x cubed to the power 1/5, right? Because we know that if we have a fractional power, this actually creates a root. And in this case, we want to find dy over dx. The first thing you want to do is employ the power rule to the outside of the function. So you're going to have 1/5, 2 plus 3x squared minus x cubed. And then you're going to subtract 1 to the power, so you get negative 4/5, because 1 is basically subtracted by minus 5/5. Then what you want to do is, so once you've found the power rule, pretend that this guy here is like a variable, right? It's basically this portion of h of x. Then what you want to do is you want to find the derivative of the inside h of x. So what we just did right now, for the first part, we actually just found the g prime of h of x. Okay, so all of this was the g prime of h of x. But then what you want to do is you want to find the derivative of h of x. In this case, you're finding the derivative of 2 plus 3x squared minus x cubed. Okay, so this portion here is the h prime of x portion. Okay, so you're going to keep this guy completely constant. I'm just going to work with this now, and then what you're going to get here is 1/5, 2 plus 3x squared minus x cubed to the power negative 4/5 times, if I do the derivative of these guys separately, this is 0. This is going to give you 6x minus 3x squared. Okay? And then what you can do is you could basically expand this, or you could basically just leave it the way it is, right? For the time being, we can just leave it the way it is. So we can actually just leave our answer. dy over dx is equal to this guy. Okay? So if you can simplify, try to do that, but if not, this is fine in this case, right? You can, the only other thing you can really do is just expand it and multiply by 1/5, but at this point, this is completely fine. Okay, let's find the derivative function of y is equal to 4x squared minus 5x to the power 4. Just by looking at this equation, you can notice that we have to use chain rule. So if I'm using chain rule, if I'm finding the derivative of y with respect to x, the first thing I want to do is I want to do the derivative of the outside, so employ power rule. So I'm going to do 4 times 4x squared minus 5x to the power of 3, and then I'm going to do the derivative of the inside. If you're doing the derivative of the inside, you get 4x squared minus 5x. Recall that we use chain rule if f of x is equal to g of x to the power of n, right? So f prime of x, or dy over dx, is basically n times g of x n minus 1, right? So in this case, and then we have to do the derivative of the inside, so g prime of x, right? So that's basically chain rule. So in this case, if I simplify this out, the derivative y with respect to x is equal to 4 times 4x squared minus 5x cubed times the derivative of this portion here, which is 8x minus 5. So if you wanted to simplify this, I'm just going to write it out here. dy over dx here is equal to 4 times 8x minus 5 times 4x squared minus 5x cubed. Okay, and you can just leave your answer like this if you wanted to expand this out. You can also do that as well, but it's really the same thing. Like if I do expand this out, you get 32x minus 20 times 4x squared minus 5x cubed. So it really means the same thing. Okay, and that's your derivative function. So you can either use that or that. All right, let's determine f double prime of 3 for the function f of x is equal to 5x squared minus 3x squared. Now, the double prime would represent the second derivative, right? So the first derivative f prime of x, you can write this as dy over dx, or the rate of change of y with respect to the rate of change of x. So the second derivative, you can actually look at the derivative of the derivative function, right? And the way we write this as d2y dx squared. Okay, so that's the second derivative function. Now, in this case, our function f of x is equal to 5x squared minus 3x, and the whole thing here is squared. The first derivative function we can determine by utilizing the chain rule. So I'm going to first use the power rule, so you get 2 times 5x squared minus 3x. Then what you do is you do the derivative of the inside, so you do the derivative of 5x squared minus 3x. So here you'll get 2 times 5x squared minus 3x, and then derivative of the inside, you'll basically get 10x minus 3. Okay, and you can leave your answer like that. There's really no point in expanding. However, you might want to think about expanding. You could think about expanding if you're looking at the second derivative, if you didn't want to use the product rule. That's really up to you. I can tend to do this both ways. You should see the same answer. So I'm just going to go with the product rule. It's a good way to kind of practice some of these derivative rules. If I was going to look at this using the product rule, right, how I would look at this, so f double prime of x is the derivative of the first derivative function, which we already kind of found here. Right? If I use the product rule, I'm going to leave the 2 out here. I'm going to do the derivative of 5x squared minus 3x. Right? We can multiply the 2 out afterwards. Right? I'm going to put the 2 in a larger bracket. Right? So you know what we could do. I don't think I need to use double brackets. So let's put the 2 out here. Derivative of 5x, I'm going to put the 2 out here fully. And just work on finding the derivative of the inside. Okay, so we'll do the derivative of the left times the right, 10x minus 3, plus the derivative of the right factor, 10x minus 3, times the left factor, 5x minus 3x. Okay, and then we're going to use the giant square bracket, right? And in this case, we basically get derivative of 5x squared minus 3x. So we're going to get 10x minus 3 times 10x minus 3 plus derivative of 10x minus 3 is 10 times 5x squared minus 3x. Okay, and what you could do is you could expand this guy out, right? So this is kind of like a squared minus b squared. So if I use the expansion, you get a squared, 100x squared, minus 2ab. So pretend this is a and this is b. Okay, so 2ab is going to be like minus 10x times 30, which is 30x times 2, which is 60x, and b squared plus 9. Okay, so that saves us a lot of time. Plus, I'm going to expand this guy out. So you get 50x squared minus 30x. Okay, so you get 2 here. This is the second derivative. And then what I'm going to do is I'm going to just kind of collect all the like terms. So you get 150x squared minus 60x minus 30x minus 90x plus 9. Okay, and that's your second derivative function. Okay, now you want to figure out the second derivative function of 3. Right, so you basically will get 2 times 150 times 3 squared minus 90 times 3 plus 9, and all I'm going to do is crunch this out in my calculator, right? And this gave us 2,178. Okay, so that's the answer for this, the second derivative of 3. And you can also do this another way, where you can actually kind of expand this guy out, right? And basically use, and then you can basically use the, you can expand out, and then you can basically just use some of the rules that we looked for polynomials, the power rule, the sum and difference rules, and so forth, and the constant rule, right? And then differentiate. Okay, so I think this one is a lot more easier, but I wanted to specifically look at the product rule because I think this would be it would just be a lot shorter in terms of the steps. Okay, so you guys can kind of try this out by differentiating, but I think I'm just gonna show you guys with the product rule. All right, let's find the derivative of this function, right? So you can actually kind of tell that this is not going to be one of our straightforward derivatives. It's going to use multiple rules together. Specifically, I'm looking at the chain and product rule, right? So let's kind of tackle this guy out. So let's just let's find m prime of x. Okay. So if we're trying to do that, I'm going to potentially be using the product rule. Now, before I actually think about finding the derivative, I'm going to write m of x as purely exponents. So you have 9 minus 2x to the power 1/2. This represents the square root. And you have x squared plus, I'm going to write this as 2 times x to the power -3 because we're using the reciprocal rule of exponents, right? So the two rules I just kind of employed, x to the power a over b is equal to the root of b, right? The index of b, the radicand x to the power a, right? And I also use x to the power -a is equal to 1 over x to the power a. Okay, so you should be familiar with some of these exponent rules. Now what we want to do here is, if I want to find the derivative function m prime of x, I'm going to do the derivative of my factor to the left here, 9 minus 2x to the power 1/2, x squared plus 2x to the power -3, plus the derivative of x squared plus 2x to the power -3 times 9 minus 2x to the power 1/2. Okay, and then what we want to do is we're going to simplify this guy out. Okay, so we're going to utilize the chain rule here, so we get 1/2 9 minus 2x. So it's really important to kind of work through this slowly. It's really easy to make a mistake here. Negative 1/2. Then what I'm going to do is I'm going to do the derivative of the inside, right? So I'm just going to separate this. 9 minus 2x. Then we're going to multiply this portion by x squared plus 2x minus 3, right? Plus the derivative of this portion here, right? So you have x squared plus 2x to the power -3, so you have 2x minus 6x to the power -4, right? And then you need to multiply this by 9 minus 2x to the power 1/2, okay? Now what we should do here is we should kind of, first let's do the derivative and simplify this a little bit further, right? So the derivative of 9 minus 2x, so we get 1/2, right? What you want to do with the negative exponents, we might want to just kind of put them on the denominator. We'll kind of work with that. So we have 1/2 9 minus 2x to the power -1/2. So I'll do that for the next step. But here we have -2, okay, times x squared plus 2x to the power -3 plus 2x minus 6x to the power -4 times 9 minus 2x to the power 1/2. Now you can already see that there is a 1/2 times -2, so this guy cancels that. So you do have a negative here, right? So what you could do here is you have a negative 1/2 here and you have a 1/2 here. Let's see if we could factor out the negative 1/2. Okay, so, and you can notice here that this one is completely different from this, right? So if you wanted to just write this as positive exponents, you could write this as x squared plus 2x to the power -3. You have 9 minus 2x to the power of 1/2 plus 2x minus 6x to the power -4. You know, our whole point here, you want to simplify this as much as possible. Okay? So if we're simplifying this as much as possible, we can understand that this is to the power of 1. Right? And in order for us to combine these functions, you need to make sure the denominators are the same. So what you could do here is you could multiply this by 9 minus 2x to the power 1/2. And I'm going to do the same thing for the denominator here. And you can notice here that because you have the same base and you're multiplying exponents, these two will add up, right? So when you do that, you basically will get x squared plus 2x minus -3 plus 2x minus 6x to the power -4 times 9 minus 2x to the power 1. Okay? And really it's up to you if you want to further expand this, but I think I'll just stop here, right? Because it would just continuously keep going. There isn't any common factors that can really expand, so I think I'm just gonna stop here in terms of the derivative function. So this is m prime of x. So you can see that this is somewhat of a complex type question. It's a lot of algebra, right? But you want to factor as much as you can and try to create as many positive exponents as you can. Obviously, I could have made another positive exponent, but I think we would just kind of stop here because this is as far as we can kind of go. Okay, so if you did want to combine these any further, you could change 2x to the power negative 3 as 2 over x cubed, and 6x to the power negative 4 as 6 over x to the power 4. But beyond that, there really wouldn't be any point in this. You wouldn't be able to factorize it any further. So we'll just kind of stop there. Alright, let's determine the equation of the tangent to the curve y is equal to 1 over the fifth root of 5x cubed minus 2x squared at x is equal to 2. So just off the bat, you guys can tell that you need to utilize chain rule for this. So to make my life easier, I'm going to change this reciprocal radical equation. I want to change it, well, this expression anyways, I want to change this into a power. So I'm going to rewrite this as 5x cubed minus 2x squared. Because it's a reciprocal, I'm going to be using the exponent rule. X to the power negative a is equal to 1 over x to the power a. So you can write this as negative to some kind of power, and because this is going to be a root, I'm going to use the rule x to the power a over b, which is equal to the index of b, the radicand x to the power a. So I'm going to put this to the power 1/5. Okay. So if you want to find the equation of tangent, we know that the slope of the tangent is basically the first derivative, so dy with respect to dx. Okay, so you want to find the derivative of this function. So when we do this, we get negative 1 over 5x cubed minus 2x squared minus 1 over 5 minus 1, which is negative 6 over 5. And then you want to utilize the chain rule where you do the derivative of the inside with respect to x. So you get 5x cubed minus 2x squared. Okay, so when you do that, you basically will get negative 1 over 5 times 5x cubed minus 2x squared to the power negative 6 over 5 times the derivative of this guy, which is going to give you 15x squared times minus 4x. Okay, and so this is your slope of the tangent, except you need to find your slope of the tangent at a single point. So I'm going to find this at x is equal to 2. So this is going to be your tangent at x is equal to 2. So when we let x equal 2, we're going to substitute 2 into all of these values. So you get negative 1 over 5 times 2 cubed minus 2 times 2 squared to the power negative 6 over 5 times 15 times 2 squared minus 4 times 2. Okay, so it is a little tedious. Okay, so I'm going to just kind of crunch all of this out. So this is negative 1 over 5, 8 times 5, 40, minus 2 squared is 4 times 2 is 8 to the power negative 6 over 5 times 15 times 4, that's 60, minus 8. So this is negative 1 over 5, 32 to the power negative 6 over 5 times 52. Okay, and if I crunch this out, well, you can notice here that this is negative 1 over 5 times the root of 5, 32 to the power 6. Okay, so it is a little messy in that sense, times 52, so I'm going to put 52 here. Okay, I'm going to crunch all of this out, and that's going to give me negative 52 times 5 times 64, which is negative 0.1625. Okay, so this is somewhat of an irregular number, but so this is the slope of the tangent. Now, using the slope of the tangent, we're going to plug this into our equation. Because the tangent is a line, we can use the equation y is equal to mx plus b. So y is equal to negative 0.1625x plus b. And you also need to substitute a point to solve for b, which is also known as the y-intercept. So to find the point, we know that x is equal to 2. Let's find its y equivalent. Okay, so let's pretend that this guy here is f of x, right? And we're going to plug in x is equal to 2 into the equation to solve for a point of y that we can plug in. So when we do that, f of 2 here is equal to, I'm just going to call this guy f of x for the time being, it's the same thing. You get 1 over 5th root, 5 times 2 cubed, minus 2 times 2 squared. Okay, and this is going to give you 1 over 5th root of 40 minus 8, which is 1 over the 5th root of 32, which we know is 1/2. Okay, so the equivalent point here is 2 and 1/2. Okay, and we're going to substitute 2 and 1/2 into the equation. So if I substitute 2 and 1/2 into this equation, we basically get 1/2 is equal to negative 0.1625 times 2 plus b, and b here is equal to, if I move this to the other side, 0.5 plus 0.1625 times 2, 0.825. Okay, so this gives us the equation of the tangent, which is y is equal to negative 0.1625x plus 0.825. Okay, and that is the equation of our tangent. Alright, the position function of a moving particle is given by s of t is equal to the cube root of t to the power 5 minus 750 t squared, where s is in meters and t is in seconds. Determine the velocity of the particle at 5 seconds. So if we're looking at the velocity function v of t is the first derivative of the position function s of t. So if we're finding the derivative of this, we can kind of just identify the fact that this basically does look like a composite function, and we have to utilize chain rule. So if we're utilizing chain rule, we're basically going to be looking at, so s prime of t here is equal to, I'm going to be using first the power rule. Before I actually do that, I'm going to just kind of clean up s of t and write it as an exponent. So you can rewrite this as t to the power 5 minus 750 t squared to the power of 1/3. Okay, so s prime of t here is basically equal to the derivative of the outside, right? So recall that if f of x is equal to g of h of x, right? This is basically the template where you would use chain rule when you have a composite function. F prime of x is equal to g prime of h of x, and then you do the derivative at the inside, so h prime of x. Okay, so I'm just using Lagrange's notation. I'm going to utilize the same thing here. So you do the derivative of the outside, so you get 1 over 3 t to the power 5 minus 750 t squared, and then you're going to subtract by 1, so you get negative 2 over 3. And then I'm going to do the derivative of the inside, so d with respect to the derivative with respect to dt, the rate of change of time, t to the power 5 minus 750 t squared. Okay, and this is going to give us s prime of t is equal to 1 over 3 t to the power 5 minus 750 t squared to the power negative 2 over 3 times 5t to the power 4 minus 150t. Okay, now we want to figure out the velocity of the particle at 5 seconds. So we're basically figuring out, so this is your velocity function, right? So you can just kind of write here that this is your velocity function. And you want to figure out the velocity at 5 seconds. So if you plug this in, you get 1 over 3, 5 to the power 5 minus 750 to the power 5, 750 times 5 squared to the power negative 2 over 3 times 5 times 5 to the power 4 minus 150 times 5. Okay, so if you want to crunch this out, right, so this is 1 over 3, this is 25 minus 750 times 25, which is 18,750 to the power negative 2 over 3, times, in this case you should see 5 to the power 5. So the numbers are quite extensive, minus 150 times 5. So this is 2,375. And if you simplify this, 25 minus 18,750, negative 18,725. So this is going to give you cube root negative 18,725 squared times 2,375. Okay, so if we crunch this out, I'm just going to put all this in a calculator. I'm going to give you guys a final answer. So I got something that looks like 2,325 over 2,115.448. And if I divide this guy out, I got 1.099. Okay, so let's just round this guy off to 1.1. Okay, so the velocity of the particle at 5 seconds approximately is 1.1 meter per second. Okay, so yeah, the numbers are a little significant in that scenario. But that's basically how you would tackle the problem. Alright, we're going to take a look at another application of the chain rule. And in this case, we want to apply the chain rule to determine dy over dx for y is equal to u times 2 minus u squared. And u is 1 over x, and x is equal to 2. Now we can notice here that u is a function of x, and y is a function of u. Okay, and we can also find a value for x as well, and x is equal to 2 here. So in this sense, if we want to find dy over dx, we understand that if y is equal to u 2 minus u squared, if we find this derivative with respect to u, we can call this dy over du. U is equal to 1 over x. If we find this derivative with respect to x, we can call this du over dx. Okay? But you want to figure out dy over dx. Well, if you want to find dy over dx, you can actually notice here that if you take dy over du and you multiply this by du over dx, right? So once again, this basically means the derivative of y with respect to du and the derivative of du with respect to dx, you can actually notice that the du's would cancel out, right? So dy over dx is equal to the derivative of y with respect to du times the derivative of u with respect to dx. Now, this basically shows us that we get dy over dx again. So I'm going to employ that. So I'm going to figure out what each of these are and then multiply together to find dy over dx. Let's first find the derivative of y with respect to du. Okay, so if we want to find the derivative of y with respect to du, to make my life easier, I could use product rule at this point, but I'm just going to expand this guy out and just use power rule. So you get 2u minus u cubed. So dy with respect to du is equal to 2 minus 3u squared. Okay, now, so that's dy with respect to du. Let's take a look at du with respect to dx, right? So in this sense, u is equal to 1 over x. So u you can write as x to the power negative 1, right? So du with respect to dx is equal to negative x to the power negative 2, okay? And as a positive exponent, it's negative 1x squared, okay? And now that you have dy and dy with respect to du and du with respect to dx, if you want to solve for dy over dx, it's equal to dy over du times du with respect to dx. These guys cancel out, and then that's going to basically be equal to 2 minus 3u squared times negative 1 over x squared, right? At this point, what you want to do here is you want to, so now you have the derivative dy over dx, but you actually have it in the form of u and x. Okay, you want to try to make sure that all the u's are in terms of x. Okay. So to do that, what you want to do is you want to do a substitution. You know that u is equal to 1 over x, right? So you're going to substitute that for u, right? So you're going to get 2 minus 3 1 over x squared, negative 1 over x squared. Okay, and when you simplify this guy out, you get 2 minus 3 x squared times negative 1 over x squared, right? Now at this point, they want you to solve for dy over dx when x is equal to 2. So I'm going to let x equal 2 here. So if you let x equal 2, you'll basically get 2 minus 3 over 2 squared times negative 1, 2 squared, which is basically 2 minus 3 over 4 times negative 1 over 4, right? And if I simplify this out, you can write 2 here as 8 over 4. So 8 over 4 minus 3 over 4 here is 5 over 4 times negative 1 over 4, and that's going to give you negative 5 over 16. Okay, so therefore dy over dx when x is equal to 2 is equal to negative 5 over 16. Right, that's the rate of change when x is equal to 2. Okay, so that's an application of the chain rule. Alright, here we're going to take a look at another question that has an application of the chain rule. So if v of s is equal to s cubed and s is equal to 3x squared minus 7x plus 1, determine dv with respect to dx, right? The derivative dv with respect to dx when x is equal to 3. Okay, so when we're looking at this question, we need to understand that in the case of the chain rule, v of s is equal to s cubed. So the derivative of v of s, which is v prime of s, you can think about this as the derivative of d with respect to ds. Okay, so it's like dv with respect to ds, which is basically the derivative of s cubed. Okay, so this is the derivative of v with respect to the rate of change of ds. Now, if we're looking at the other function, this is basically s of x, because s is a function of x. We get 3x squared minus 7x plus 1. If we find a derivative of s of x, we're basically finding ds with respect to dx, right? So this is the first derivative of s of x, s prime of x, and we can basically calculate each of these, right? So it's basically the derivative with respect to dx of 3x squared minus 7x plus 1. Now we want to figure out dv, the rate of change of v with respect to the rate of change of x, right? So dv with respect to dx. In order to do this, we need to basically multiply the derivative of v with respect to s by the derivative of s with respect to x. And you can notice here that these two would cancel out and you actually get dv over dx. So dv over dx is going to be equal to the derivative of dv over ds, which is the derivative of s cubed, and we'll multiply this with the derivative with respect to x of 3x squared minus 7x plus 1. Okay, so when we're doing this, we're basically going to find the derivative of each with respect to each of the variables. So we have s cubed, the derivative with respect to ds, so we get 3s squared times the derivative of this polynomial. We're going to be using the combination of the sum and difference rule. So we'll get 6x minus 7. Okay, so this is dv over dx. And in this case, what's going to happen here is we want to figure out dv. Oops, I wrote y instead of v, sorry. So we want to figure out dv, the rate of change of v with respect to x, when x is equal to 3. Okay, so in order to do that, we need to kind of get rid of this s variable. So we can notice here that s is equal to 3x squared minus 7x. plus 1. Now you could do this one of two ways. You can either just plug this in, or what you could do is you could plug in s of 3 into s, right? So you think about this as s of x. S of 3, which is equal to 3 times 3 squared minus 7 times 3 plus 1, which is equal to 27 minus 21 plus 1, which is basically 7. So s of 3 is equal to 7, but we can actually plug in this value into s. Okay, so because we're going to eventually plug in s in terms of x either way, it's just going to be the same thing. So this is 3 times 7 squared times, now I'm going to plug in, everywhere I see x, I'm going to plug in 6. So you get 6 times 3 minus 7. So this is going to basically be dv over dx when x is equal to 3 is equal to 49 times 3 times 18 minus 7, which is 11. And if I punch all this out, you should get 1617. Okay, so therefore dv over dx when x is equal to 3 is equal to 1617. Okay, and that's the rate of change when x is equal to 3. Alright, let's apply the chain rule in Leibniz's notation to determine dy over dx at the indicated value of x. And here's your equation: y is equal to u squared plus 3u, u is equal to square root of x minus 1, and x is equal to 5. So technically what we're trying to do here, find dy over dx when x is equal to 5. Right, we can see that we have to utilize the chain rule, right, because y is a function of u and u is a function of x, right? If you actually plugged in this equation into y, I'm just going to do this for an experimental purpose. So you have u is equal to square root of x minus 1, y is equal to u squared, so square root of x minus 1 for u. I'm going to substitute that in. I'm going to just write y in terms of x. This is another alternative way you can do this, right? But I'd rather you guys use chain rule. The reason I'm doing it this way is because I want to show you guys the domain and range, because it is going to be really useful to us later on when we find a derivative. So in this case, your equation here would be x minus 1 plus 3 square root of x minus 1. Okay, and you can see that the domain here, x belongs to all real numbers, but x has to be greater or equal to 1, right? Because we know that this portion here, the radicand, it can't be negative, right? So the lowest value you can have is x is equal to 1. So if the lowest value you can have is x is equal to 1, right? Then the range here, if x is equal to 1, 1 minus 1 is 0, and 1 minus 1 here is 0, so the y value would actually be 0. So y will always be greater or equal to 0. So keep this in mind. And I'm going to show you guys how to do the chain rule here for this question. We want to find dy over dx. Well, if you actually find dy du and you multiply it, right, and this dy over du is the derivative of y with respect to u, which is this function. You multiply this with the derivative of u with respect to dx, or with respect to x, you can actually see that you can cancel out and you get dy over dx. Okay, so let's find each of these derivatives first. Okay, so let's find the derivative of y with respect to u. So this is basically the derivative of u squared with respect to u plus the derivative of 3u with respect to u, and this is 2u plus 3. So this is the derivative of dy with respect to du. Next thing you want to do here is let's look at u as a function of x. U as a function of x here is equal to, and you can write this as x minus 1 to the power 1/2. I'm just going to write it as a power. So du with respect to dx is equal to 1/2 x minus 1 to the power negative 1/2 times the derivative of the inside, which is the chain rule, but we can understand that this is 1. Okay, so now we have the derivative here. I'm going to change this to just positive exponents, so you can write this as 1 over 2 square root of x minus 1, right, because the negative 1/2 is the reciprocal. And if I combine these together, right, if I combine this guy and this guy together, dy over dx is dy over du times du over dx, right? So you get dy over du, 2u plus 3 times 1 over 2 square root x minus 1. Okay, and in this case what you want to do here is you want to substitute u here for square root of x minus 1. So you can write this as dy over dx is equal to 2 square root x minus 1 plus 3 over 2 square root x minus 1. Okay, now we can note here that the domain and the range here contain restrictions. Okay, and specifically we wanted to find the value of dy over dx when x is equal to, and I think I should put the line here actually, but x is equal to 5. So if I plug that in for x equal to 5, you get 2 times 5 minus 1 plus 3 and 2 times 5 minus 1, right? And we know that square roots are positive and negative, but because y has to be greater or equal to 0, we can only have positive values of the square root function. So we can actually have 2 times square root 5 minus 1, which is basically 2 times 4 plus 3. So I'm just going to look at the positive values. 2 times square root of 4, not 4, but square root of 4. And in this case, you get 2 times 2 plus 3. So only look at the positive values of square roots. And you get 2 times 2, which is 7 over 4. So that is your slope, right? So therefore, dy over dx when x is equal to 5 is equal to 7 over 4. So because of the restriction on the range and the restriction on the domain, y has to be greater or equal to 0 and x has to be greater or equal to 1. So because of that, you can only have the positive value of the square roots here. Okay, so that's our answer. All right, let's take a look at another example of the use of the chain rule. So here we have considering y is equal to u cubed over u squared plus 1 and u is equal to 3x minus x squared. Determine dy over dx when x is equal to 2. Okay, so recall that chain rule is utilized when we essentially have composition of functions or a composite function, right? So if we want to basically find the derivative of this function, y is equal to u cubed over u squared plus 1, then the derivative would be the rate of change of y with respect to u, right? If we wanted to find the derivative of this function, u is equal to 3x minus x squared, we would find this derivative as du with respect to dx, right? So chances are if we actually take these two derivatives and we multiply it together and we actually take a look at Leibniz's notation, you can actually notice that you actually get dy over dx, right? So that's the rate of change of y with respect to x. So this is basically a template that we're going to be using. We're going to find each of these derivatives and then we're going to multiply it together. Then we're going to basically substitute x is equal to 2 into the derivative function. So let's first find the derivative of y with respect to u, right? dy over du. And you're going to have to utilize chain rule here. So first I'm going to do is I'm going to do the derivative of the numerator. So you get u cubed times the denominator u squared plus 1 minus the derivative of the denominator, which is d over du, u squared plus 1 times the numerator u cubed. And then this is going to be divided by u squared plus 1 squared. Okay? So when I do the derivative of the numerators, what you're going to see here is you're going to see 3u squared times u squared plus 1 minus 2u times u cubed. Okay, that's just basically the numerator portion. What I want to do here is I'm just going to simplify the numerator before I actually put the denominator down. So I'm just going to expand this guy out. Right, so you get 3u squared times u squared, which is 3u to the power 4, plus 3u squared minus 2u to the power 4, right? So I can combine these two together because these are both like terms, right? So 3u to the power 4 minus 2u to the power 4, you get u to the power 4 plus 3u squared, okay? So basically what your derivative function, I'm just going to write it here, dy with respect to du is basically going to be equal to u to the power 4 plus 3u squared over u squared plus 1 squared. Okay, so that's what your derivative of y with respect to u is. Now if we want to find the derivative of u with respect to x, then what you want to do here is basically you want to do the derivative of this guy, so the derivative of 3x minus x squared with respect to x. And what you're going to see here is you're going to get 3 minus 2x, right? So du over dx is equal to this, right? 3 minus 2x. And then what you want to do here is you want to multiply the two, right? So you have dy over du times du over dx, which is going to give you dy over dx, okay? Now when you do this, what you're going to see here is, let's see what happens here. So what you're going to see here is you're going to get u to the power 4 plus 3u squared over u squared plus 1 squared times 3 minus 2x, right? But we need to also understand that we need to find the derivative where x is equal to 2, okay? So this is a derivative function. All you have to do, and just make your life a lot easier, let's figure out what the value of u is going to be when x is equal to 2. So if x is equal to 2, u is going to be, and you're going to plug it into this equation here, okay? U is equal to 3 times 2 minus 2 squared, which is 6 minus 4, which is basically 2. So u is going to be equal to 2, right? X is also going to be equal to 2. So if I plug this in, you basically get 2 to the power 4 plus 3 times 2 squared over 2 squared plus 1 squared times 3 minus 2 times 2. And that's going to give us 16 plus 12 over 4 plus 1, which is 5 squared, which is 25. And this is times 3 minus, this is 4 basically, right? So 3 minus 4, which is negative 1, right? And this is basically 28 over 25, right? So this is negative 28 over 25, and that's our answer, right? This is basically dy over dx when x is equal to 2, okay? And that's basically our rate of change, or that's our slope at x is equal to 2. All right, we're going to take a look at another rule of differentiation, and this one is called the quotient rule. So you use the quotient rule if a function q of x can be written as f of x over g of x, and you can notice here that if you do the derivative, g prime of x cannot equal 0. In this case, g of x cannot also equal 0, so we should kind of write that in as well. Right, that would basically be a restriction. Now, in this case, the derivative of any function that can be written as a quotient of two different functions, q prime of x is equal to the derivative of the numerator f of x, so f prime of x, times g of x, so times the denominator, minus the derivative of the denominator, g of x, g prime of x, times the numerator f of x. And this is all going to be divided over the denominator squared. Okay, so I'm going to show you guys an example of this template. So this is going to be the template that we're going to be using. So make sure you guys copy this down. But I'm going to show you guys how to use this, and we'll do several examples regarding this. Whoops. Well, that just kind of got rid of my box. Okay, so I'm going to show you guys how to use this template, and we're going to differentiate this to kind of demonstrate that. Okay, so let's say we want to differentiate y is equal to x to the power 4 divided by x squared minus x plus 1. So in this case, if I want to find the derivative with respect to x, dy over dx, I'm going to first do the derivative of the numerator. So I'm doing the derivative of f of x, so f prime of x, so the derivative of the numerator, x to the power 4, okay, times the denominator, x squared minus x plus 1, minus the derivative of the denominator, x squared minus x plus 1, times the numerator, x to the power 4, and divide all of this by x squared minus x plus 1 squared. Okay, now what I'm going to do is I'm going to clean this up, and I'm going to just find the derivative of each. So the derivative of x to the power 4 is 4x cubed times x squared minus x plus 1 minus the derivative of this guy. X squared is basically 2x minus 1 times x to the power 4. And notice I'm putting brackets, right? Because we need to make sure that we do this appropriately under the principles of BEDMAS. You get x squared minus x plus 1 squared. And what I'm going to do here is I'm going to just kind of expand out these terms and then make it a lot nicer to look at. Right, simplify it out. dy over dx. So you can notice here that there's considerable amount of algebra when you're looking at differentiating, so make sure you're okay with the algebra. So this is 4x cubed times x squared, x to the power 5, minus 4x to the power 4, plus 4x cubed, minus, and I'm just going to expand this guy out first. Okay, so you get 2x to the power 5 minus x to the power 4. And this is going to give us, I'm just going to work with the numerator for the time being. Okay. But you can kind of write the denominator out here. We don't have to expand the denominator, we'll just leave it the way it is. And this basically gives us 4x to the power 5 minus 4x to the power 4 plus 4x cubed minus 2x to the power 5 plus x to the power 4. Right, I'm going to collect the like terms. I'm going to collect this guy and this guy, so I'm just going to kind of work with the numerator right now. And I'm going to collect this guy here with this guy. So this is going to give us 2x to the power 5, negative 4x to the power 4 plus 4x to the power 4, plus x to the power 4, sorry, negative 3x to the power 4 plus 4x cubed. Okay, so this is what the numerator will look like, and this is our denominator. So you can rewrite this guy, dy over dx is equal to, and what you could do here is you could expand out, you could factor out the x cubed. You get 2x squared minus 3x plus 4, and this is over x squared plus x plus 1 squared. Okay, you might always want to check to see if you could factor the inside of this. In this case you really can't, but in some cases it will help you simplify it a lot easier. And this is basically your derivative, okay, dy over dx. Okay, so we'll look at a few more questions regarding the quotient rule. Okay, let's find the derivative function of f of x. So we want to find f prime of x. Okay, so in order to do that, what I'm going to do here is I'm going to use the quotient rule because it does look like a rational expression where f of x looks like g of x over h of x. Okay, so if I'm using the quotient rule, f prime of x is equal to the derivative of the numerator g prime of x times the denominator h of x minus the derivative of the denominator h prime of x times the numerator g of x, and this is going to be over h of x, the denominator squared. Okay, so if I'm finding the derivative here, if I'm using this template, f prime of x is equal to the derivative of 3x minus 1 times x plus 5 minus the derivative of x plus 5 times 3x minus 1, and this is going to be over x plus 5 squared on our denominator. So I'm looking at the derivative. If I clean this up a little bit, the derivative of 3x minus 1 is 3 times x plus 5 minus the derivative of x plus 5 here is 1 times 3x minus 1. I'm just going to work on simplifying the numerator first, and then I'm going to combine the denominator. So if I expand this guy out, this is 3x plus 15 minus 3x plus 1. In this case, excuse me, 3x minus 3 is 0, and then you get 15 plus 1 is 16. Okay, so this is after I've simplified the numerator, and if I combine this together, so this is the numerator, if I combine this together, f prime of x is equal to 16 over x plus 5 squared. Okay, so that is the derivative function. Alright, let's determine the equation of the tangent to the curve y is equal to x cubed minus 1 over x plus 2 squared at the point x is equal to negative 1. So to do this, we're basically going to be finding To find the equation of the tangent, we need to find the slope of the tangent, as well as the y-intercept. So let's start with the slope of the tangent, which is basically the first derivative of our function, rate of change of y with respect to x. Now in this case we need to actually utilize chain rule. So if we're using chain rule, I'm going to do the derivative of the outside, 2. You have x cubed minus 1 over x plus 2 to power 1, but then you have to do the derivative of the inside. Now the derivative of the inside is basically something that appears as a quotient of two functions. You have x cubed minus 1 divided by x plus 2. So we actually have to employ the quotient rule. So I'm going to do the quotient rule out here separately, right? And recall that to find the quotient rule, you need to do the derivative of the numerator, which is x cubed minus 1 times the denominator, x plus 2, minus the derivative of the denominator, x plus 2, times the numerator, you have x cubed minus 1, and you're going to divide this by x plus 2 squared. So if I clean this up by finding the derivative of x cubed minus 1 is 3x squared times x plus 2. I'm just going to look at the numerator for the time being. So this is just the numerator, right? Minus the derivative of x plus 2 is 1 times x cubed minus 1. And if I just clean this up by expanding it, so this is 3x cubed plus 6x squared minus x cubed plus 1. So you basically get 3x cubed minus x cubed plus 6x squared plus 1, which is equal to 2x cubed plus 6x squared plus 1. Okay, and all of this, all of this is going to be over x plus 2 squared. Okay, so this is what the derivative of x cubed minus 1 divided by x plus 2 looks like. And then what we want to do is we want to collect these two together, right? So therefore dy over dx should be equal to 2 times x cubed minus 1 over x plus 2 times 2x squared, 2x cubed plus 6x plus 1 divided by x plus 2 squared. Okay, now if you want to collect the two terms, right, you can notice here that there's an x plus 2 here and x plus 2 squared here, so you actually need to you actually need to make sure that the denominators are the same. But because you're multiplying it, you can just kind of plug it in, right? So in this case, you get 2x cubed minus 2 times 2x cubed plus 6x plus 1 over x plus 2 squared, cubed, sorry. Okay, and this is basically your derivative. Now you actually don't need to expand this out because we want to figure out the point at -1. No, this is too choppy, man. Alright, let's determine the equation of the tangent to y is equal to -x over x plus 1 squared at x is equal to -2. So if we want to find the equation of the tangent of a tangent is, well, we know that tangent is a line, so it should be in the form of y is equal to mx plus b, right? Now we want to find two things out of this equation. We need to find the slope of the tangent and the y-intercept, right? Now in order to do this, it would help us to have a point. We know that x is equal to -2. I'm going to find the equivalent y value to this point. So if I plug this in, I'm going to call y f of x. So I'm going to do f of -2 to find its equivalent y value. So we have -2 over -2 plus 1 squared, which is 2 over -1 squared, which is 2. Okay, so our point here is -2 and 2. So this is the point that the tangent is going to hit. Now, in order for us to find the slope of the tangent, we need to find the derivative function f prime of x, but we're specifically finding the slope of the tangent at x is equal to -2. So we're basically finding f prime of -2. So f prime of -2 just means the slope of the tangent at x is equal to -2. So let's find the derivative function. So f prime of x here, we know that f of x is equal to -x over x plus 1 squared. To find f prime of x, I'm going to be using the quotient rule. So I'm going to do derivative of -x. Oops. -x. So derivative of numerator times the denominator, x plus 1 squared, minus the derivative of the denominator times the numerator, -x. I'm going to put this over to the denominator squared, so x plus 1. If you square x plus 1 squared, you get x plus 1 to the power 4. Okay, if I clean up the numerator a little bit, we get -1 times x plus 1 squared minus, you're going to be using the chain rule here, so 2 times x plus 1. Because the derivative of the inside of this is 1, we don't have to write it, times -x. And if I simplify this, I'm going to factor out an x plus 1 here. So if I factor out an x plus 1, we get -1 times x plus 1 times -2 times -x. And this is going to give me x plus 1 times -x minus 1. So I'm going to expand this guy out. So it's always good to kind of factor this out because it will make our expression more simplified and it's easier to work with. This is x plus 1 times -x plus 2x, which is x minus 1. Okay, so this is what the numerator looks like. So our derivative function f prime of x should be x plus 1 times x minus 1 over x plus 1 to the power 4. Now at this point, I'm just going to simplify this a little bit. So I'm just going to move it over here. So if I simplify this, I can divide the common factors. This is power 1, this is power 4. So we basically have f prime of x minus 1 over x plus 1 to the power of 3. Okay, so you want to find the slope at this point. So I'm going to do f prime of -2. Okay, so you want to find the slope at -2. So f prime of -2 is -2 minus 1 over -2 plus 1 cubed, which is -3 over -1 cubed, which is positive 3. Okay, so f prime of -2 is positive 3. So the equation here is y is equal to 3x plus b. Okay, you want to solve for b now, right? We have the slope. If you want to solve for b, you're going to substitute a point because we know that a tangent only passes through a single point, and any point that passes through a line will satisfy the equation of the line. So we're going to substitute the point -2 and 2 because that's the only point that actually passes, that this line will pass through. So if I plug this in, we basically get 2 for y is equal to 3 times -2 plus b, and this is going to give us 2 is equal to -6 plus b. B is equal to 8. So therefore, so we have b is equal to 8, we have slope is equal to 3, so the equation of the tangent, therefore, is y is equal to 3x plus 8. Okay, so that is the equation of the tangent to the